Hello everyone, welcome to our talk. I'm Liu Wei from Tencent Security Shadow Lab. Now, I and my colleague Wu Zekai will share our research on undefined behavior optimizations in LLVM. We are researchers from Tencent Security Shadow Lab to better understand threat landscape and protect our user data and infrastructure. Our lab focuses on applied research in both software and hardware. This work is conducted by Wu Zekai, Liu Wei, Liang Mingyue, and Song Kai. All of us are members of foundational security research team in Tencent Security Shadow Lab. Okay, let's start. Here is a quiz. The read function calls the internal read function to get the content of the internal array. There is an array bound check in function internal read. A null point will be returned if the bound check failed, but the read function doesn't check the return value of internal read function. It should trigger a null point dereference undefined behavior if we try to read out of bound. Now we compile the program with clan and it crashed as expected. However, if we compile the same program with high optimization level, surprisingly, the program will not crash. And will even output an out-of-bound read result. What happened? To better understand it, let's enter the world of undefined behavior and see the magic of LLVM. In this talk, we will first introduce backgrounds of undefined behavior in LLVM. Then, we will discuss how to detect undefined behavior and analyze some of the bugs we found. We will demonstrate our exploit on Chromium using a non-point dereference undefined behavior bug. And last, we'll give our suggestions and make a conclusion. What's undefined behavior? According to the C standard, it's behavior upon use of a non-portable or erroneous program construct or of erroneous state. The standard imposes no requirements for undefined behavior. The C and C++ has lots of undefined behavior. 211 undefined behaviors appear in C17 standard, and more new undefined behaviors will be added in the near future. Here are some common undefined behaviors, such as non-pointing dereference divided by 0, array index out-of-bound access, oversize shift, uninitialized usage, signed integer flow. Most of them are typical security issues. What is LLVM? LLVM is a popular compiler infrastructure. It provides the language-independent and target-independent intermediate representations. It gives us high-quality libraries including optimizations, analysis, code generators, profilings, and debugging. Most of us may be more familiar with their sub-project products, such as Clan, the LLVM native compiler. It builds a large number of products, including Chromium, Firefox, Android Framework, and iOS kernel. LLVM also has undefined behaviors. They fall into 3 categories. First of them are true undefined behavior. It represents serious errors like dividing by 0 or illegal memory access. The second are called undef. They usually come from uninitialized value. The third kind are poison. They are introduced by compilers themselves. They are used to support speculative executions. We will discuss on finding true undefined behaviors in a speech. What's the consequence of executing undefined behavior? Actually, anything is possible. Maybe nothing wrong happens, the program works as expected. Or it may fail to compile or output an non-predictable or nonsensical result, or even it will crash. Sometimes crash means a security vulnerability occurs. For example, undefined behavior such as array index out-of-bound error will lead to memory corruptions directly. Another concerned security threat is more hidden. Sanity checks may be removed if it contains undefined behavior code. So we need to find ways to detect the undefined behavior. Next part, we'll discuss the detections. Existing detections methods can be classified into two categories: static analysis and dynamic analysis. Dynamic analysis are usually fuzzy. Various sanitizers help a lot. For instance, undefined behavior sanitizer can detect shift errors, sign interval flow, non-point dereference, and so on. Address sanitizers can detect out-of-bound access memory corruptions. Memory sanitizers can detect uninitialized usage. But these tools require appropriate test cases to trigger the bugs. As for static analysis, compilers will output warnings for definite undefined behavior. With double error flag, we can stop compiling when undefined behavior has been detected. Static analysis tools like Static Analyze and Coverity has a lot of checkers to scan the specific undefined behavior. But these tools only detect a fraction of undefined behavior, and they don't make the best use of compilers' analysis on programs. Is there any simple but effective way to detect undefined behavior? Let's turn back to a quiz for inspiration. I disassemble the executable and find there are no bound check branches in function main at all. The out-of-bound read value has already been fetched. We are still very confused what happened. We dump the LLVM intermediate representations to take a deep look. We found that the bound checking instruction is missing in function read even before it is in line to function main. So we should focus on function read. After comparing either of the two different optimization passes, we found that the bound check instructions are removed in optimization path called combine redundant instructions. This path is used to remove redundant instructions. When loading a address which come from a select instruction, the non-point branch will be abandoned. LLVM found this undefined behavior bug when analyzing the program, but they don't tell you. They simply fold it. What's worse, an out-of-bound access vulnerability appears due to these optimizations. What do we learn from the quiz? The key point is the LLVM actually finds the undefined behavior, but they just don't tell the programmers. They tend to automate undefined behavior code themselves, and sometimes even create security vulnerabilities. Since LLVM is capable to find lots of undefined behavior, why not just use its findings? Let's go back to the combined redundant instruction optimization path. We can add hooks here so that we can check where undefined behavior happens. We can use the hood clan to compile the program and find the undefined behavior bugs. You may challenge me that this detection is a little limited, as only a non-point dereference in select instruction can be found. So we should add more hooks. It's a little bit challenging to locate well-to-do instrumentations. LLVM has a large codebase of over 6 million lines. It's hard to read them all. Another problem is that the different kinds of undefined behavior are mixed up together. We have to distinguish the true undefined behavior that has security impact. Our method is to combine source review with manual experiments. We focus on finding undefined behavior that has secret thread. It can be divided into two categories. The first kind of bugs appears when program schematics are changed incorrectly. The second kind are security vulnerabilities themselves. We start with the first case. Inspired by the previous quiz, we first focus on select instructions. These are some code snippets where undefined behavior will be folded in select instructions. Listing optimizations will change the control flow graph by removing undefined behavior instructions. Branch instruction is similar to select instruction. If a branch contains undefined behavior, it will be removed. If a deleted branch is used for sanity check, it will lead to security bugs. Another approach is to find undefined behavior bugs that are security vulnerabilities themselves. You will first think of array index out-of-bound bugs. They are powerful, but they need to precise static analysis and a hard to model. We can choose other appropriate type of undefined behavior, such as integer overflow and uninitialized usage. If we have difficulties in locating LLVM's undefined behavior handling code, we can write vulnerable test cases to help us understand LLVM's code. For example, in function test, we write an integer overflow sanity check, but the comparison contains undefined behavior. If clan compile it in default configuration, the sanity check works. But in a higher optimization level, the control flow graph of the program has changed. The integer flow will be removed. How does this happen? In LLVM, when x plus y will be integer flow undefined behavior, the comparison between x plus y and x can be simplified to comparisons between 1 and 0. If we add instrumentation here, we can find potential integral flow bugs. This is another integral flow case. The function test will compute the shift results of inputs. In common sense, the output result should be 0 when the input is x and y are both 0. But if we perform level 3 optimizations, the output is not 0. If we observe the program more carefully, we will find there exists an oversized shift undefined behavior. We can check binary operations of undef to find the potential overflow. In addition, the arithmetic operations with undef sometimes returns abnormal values. It may cause vulnerabilities too. We can use similar method to find LLVM's handling code. Instrumentations here help us find undefined behavior folded in binary instructions. After sharing our detection method, you may wonder the false positive rate of the log. We can automatically filter false positives brought by present undefined behavior and select the cases where we can control input to trigger the undefined behavior set effect. Then most of the output should be the true undefined behavior we anticipate. Okay, let me sum up our detection approach. First, we dig into LLVM internals to figure out LLVM's undefined behavior handling code and add instrumentations to log the undefined behavior info found by LLVM. Then, we can use hooked clan to compile programs to scan the undefined behavior bugs. After filtering false positives, we can start to construct proof of concept to trigger the bugs. We have used all tools to scan Chromium and Android frameworks and found lots of bugs. Now, I will hand it over to Zekai. He will share the detection result with us.
Thanks. I will analyze several typical vulnerabilities found by our tools. CVE 2020-0452 is a bug in lib.dxii, which is a library to edit DXII file. In this function, it will check whether the size of variable e plus size of assigned shot would overflow. The check works well in autocompilers, but LLVM, since it is a defined behavior, it will be simplified to a comparison between size of assigned shot and 0, which is always true. As a result, the sanity check is removed, and it gives rise to heap overflow in memory copy function. This CVE is not an isolated case. There are many similar history bugs in the same library, as shown in the figure. The root cause of this CVE is conducting sanity check with undefined behavior code. LLVM will remove them. As a result, none of the expected sanity checks will take effect. What a shock. Using undefined behavior to do sanity check seems to be a popular programming paradigm and works well in autocompilers. But they lead to vulnerabilities in modern heavily optimized compilers like Line. More importantly, these old libraries are still widely used. For instance, LibEXIF was first released in 2002, but is still integrated in Android Media Framework now. Okay, let's test. This is a code snippet of Sphere, a popular open source two-dimensional graphics library. Here is the integer overflow in multiplication. We found this bug in transient constant folding of undefined behavior. The overflow set is used to allocate buffer, which leads to a heap buffer overflow vulnerability. Bug 1071311 is also in Sphere. It is similar to the quiz. The set function uses the return value of the internal get function to do an OR operation. In internal get function, a non-pointer will be returned into the bound check file. Non-pointer dereference is the undefined behavior. LLVM will remove the branch so that the check won't take effect. We can pass a live index to trigger an auto-bound write. Bug 1076387 is in Blink, the rendering engine used by Chromium. It's a constructor of WebGL timer query ext. It will use the return value of canvas function to call getDocument function. In canvas function, it will check the host type or decide to return non-pointer or cast the host to HTML canvas element and return its address. Call from non-pointer is an undefined behavior. LLVM will remove the branch so that we can confuse offering canvas with HTML canvas element. To demonstrate the security threat of undefined behavior, we select one of those vulnerabilities to write an exploit. We successfully achieve remote code execution on Chrome browser with a single undefined behavior tag. This is Chrome bug 1076387, shared in the previous slide. An off-screen canvas is incorrectly cast to HTML canvas element. Here is the disassembled code of this function. When the object is HTML canvas element, RX minus 90 refers to its map. The off-screen canvas is smaller than HTML canvas element. When the type confusion occurs, RX minus 90 will skip it and point to the memory box. After type confusion occurs, the incorrectly fetched value will be passed to core instruction, so we can control RIP. The detailed relationship is shown on the slide. To control the value of VV, we should be able to set the value of YY first. That's the job of heap function. A screen canvas is a garbage collected object in Blink. Blink uses OilPan to manage garbage collected objects. In OilPan, objects are divided into 4 categories. They go to different buckets depending on their size. The screen canvas is located in the normal page arenas. The size of a screen canvas is C0, so we have to find the object located at the 64 to 128 bytes bucket, normal page arenas. Another requirement is the value of YY can be controlled. How to find it? We can use code QL to find objects located in the right memory track. Then we have to review the source code to confirm whether the value of YY can be controlled. Fortunately, we found the IDB OpenDB request object that meets these requirements. The version number of the object is at the right position and can be controlled. When we successfully occupy the memory, the RAX register can be successfully controlled. But to control RIP, we still need to fix the heap layout. We can try to exploit the 32-bit room. 32-bit room has a smaller memory address space. Heap spray technique can make it easier to control EIP. The IDB OpenDB request object under 32-bit no longer meet our requirements. We need to find a new suitable object in 32-bit room using the SIM13 method. We found the offline audio context object. The length number of the object is at the right position and can be controlled. But when offline audio context is created, another audio handler object will be created in this construction. The following graph shows the memory layout. Audio handler is a LLVM object call. Fortunately, we can bypass it through heap function. All pan use freelist to manage free memory. So we can create an object of the same size as offline audio context next to a screen canvas. Free it, and now this memory is managed by the freelist. Create offline audio context. It will use the previously freed memory. We found the media theme object with the same size as offline audio context. After heap function, we can successfully control the value of EAX register. After that, we can use heap spread technique to control EIP. The offset address under 32-bit is different. The spread structure is shown as in the figure. After triggering the vulnerability, the value of RX register will be sleep. Then it will be dereferenced and go back to sleep, so that we can smoothly change EIP to whatever value we want. Next step is to do ROP, but it needs another byte to this base address of chromo.dev. Can we find an approach to execute code in memory without help of invalid vulnerabilities? GIT sparing circumvents the protection of ASLR and DEP by exploiting the behavior of just-in-time compilation. The purpose of GIT is to produce executable data. The input program typically contains numerous content values that can be erroneously executed as code. For example, we write such a piece of JS code. When it is compiled into assembly code by GIT, it will look like this. If we jump to GIT code with offset, the code will become weird. Some of the data will be executed as code. This means that we can control the executed code by changing the date. Now, let's make some changes to the original JS code. You can see the generated assembly code is as follows. After we add an offset to this code, A8 and the 35 are merged into a capital AL 3935 instruction. The following 390 is treated as 3 not instructions. This means that 3 bytes in every 5 bytes can be used in code instruction. We can use those instructions to construct a shellcode. In this way, our shellcode is allocated at the executable memory area. We can spread such GIT code chunks into the memory and change the EIP register to the address. Then we can execute our shellcode. There are many tricks in GIT spreading. Be careful of the encoding of XOR operation. XOR EX instruction only needs 1 byte. It's a perfect gadget. XOR other registers all need 2 bytes and can't be used as shellcode. We can change the format of XOR statement to select the suitable register. There are the demo we exploit the Chrome of stable version 79. We successfully abused an undefined behavior bug to achieve remote code execution. Finally, its conclusions. Firstly, we have some suggestions. For programmers, to understand undefined behavior and resolve this undefined behavior bugs. For compiler developers, to provide more accurate and useful undefined behavior warnings to programmers. For bug hunters, to get more useful undefined behavior info from compilers. In this talk, firstly, we illustrate how to utilize compilers' ability to find undefined behavior bugs. Then we explain several security bugs caused by undefined behavior. Finally, share advanced Chrome exploration techniques. Special thanks to Huiming Liu and Chuan Dadi. Thanks.